My thesis research is about deep learning on medical imaging. When I was asked to give this talk, I really wanted to talk about something matters to queer community. And as far as I learned, language matters, and the applications of language also makes much more impact than technical research. So I chose NLP and machine translation task as part of this talk. So I'll be talking about that. The first attempts of machine translation started with rule-based models, as you see from here, and then statistical-based models emerged, and then currently we're using neural machine translation models. Rule-based models are using several set of rules to understand the language and help the translation. It can use some transliterators and correctors as well. Direct machine translation, transfer-based machine translation, and interlingua are the subsets of the rule-based machine translation. There are several limits in this space. It's always not feasible to generate rules of the language and use them. The translation it's not really feasible. So instead of that, statistical approaches emerged. Statistical approaches aims to generate the inner rules of the language without inner structure of the language using statistics. And during the last year's statistical approaches were the most used machine translation methodologies. These methodologies require alignment of words, building n-grams, aligning each sentence, which can be or may not be possible for may not be possible for every language. So it's necessary to come up with a general solution. So neural machine translation developed. Neural machine translation uses neurons to learn the statistical model necessary for machine translation, which works in similar to style transfer, learns the style of the input language and transfer this to the output language. And neural machine translation is considered as an end-to-end system. There is an encoder network, encodes the sentence-specific set of features, and mostly RNNs, LSTMs, and GRUs used in these neural machine translation systems. Recurrent neural networks are inherently sequential, and this property prevents parallelization within training examples. And for longer sequence lengths examples, sequential computation brings computational management issues. And sec-to-sec with intelligent use of attention mechanism tried to overcome these computational issues, but still it was necessary to generate, use parallel corpora to make efficient machine translation. And there's still computational limitation of the sequence length. If the sequence length is longer, the sec-to-sec models fails to work efficiently. So transformer architectures emerge. Last of the well-known NLP research is now based on transformer architecture. The transformer architecture contains multi-head attention and a feed-forward neural network. Encoder has 2 layers and the decoder has 3 layers. Same as the encoder's 2 layers on top of a multi-head attention. Multi-head attention mechanism is the bigger and efficient version of the scaled traditional attention mechanism. And it's using linear projection of the queries, keys, and values with respect to attention heads. And allows model jointly attend to information from different representation subspaces and different positions. It has increased representation but reduced dimensions, so computational cost is similar to singlet attention. These are the... and for the recent models, pre-training of model is the very recent application of machine translation. No, NLP and the machine translation. It works like randomly masking input tokens from input and the predicting these masks from the using decoder network. Mask models allows bidirectional pre-training on transformer and the BERT and the similar state-of-the-art models using this masked language modeling technique. From the previous models, there is a need of some guidance in data. The data set needs to be aligned, needs to be, there's always need of parallel corpora in classical approaches. And when there is a low resource language, it's really hard to come up with a general translatable general solution for machine translation. So using monolingual corpora and without supervision, it can be better for, but it can provide better translation for low resource languages, and it can overcome the challenges of the machine translation. Unsupervised machine translation uses only monolingual corpora. There is no parallel data available. There is a shared encoder of the language and independent representation of the input. There is also the back translation task. The back translation happens during the pre-training, and it generates pseudo parallel sentence pairs. So it allows the machine translation to occur. This is the back translation algorithm of first pre-training and the back translate and the translation reconstruction. In this task for masked language modeling, we sampled byte pair tokens. 80% of byte pair tokens with masked and rest stayed random, and the other ones unchanged. This way, masked language modeling allows the use of text stream arbitrary number of sentences, not pairs. Subsampling helps the balance in the rare sentences, which is also one of the mainstream problems in the machine translation. When there is an unbalance, it fails. So it helps the balancing of the rare sentences, or rare sentences could be translated to another language. Pre-training cross-lingual word embedding generates the cross-lingual model of the system. So it also represents the earlier idea of the interlingua. This is how mask pre-training works. There are language and position and token embeddings, and token embeddings. Some of the token embeddings randomly masked. it also happens on the translation part. The embeddings are randomly masked, and the model works together to make in this random masking translation. In this work, we did unsupervised mass pre-training of the transformer model on low-resource languages. Low-resource genderless languages. English also a genderless language. I should also remind you the notion of genderless languages. Genderless languages are, they don't have, in their grammar there is no notion of gender. English, Turkish, Turkic languages, African, Finnish, and Basque, and there are also similar languages are genderless. The problem here is the translating to gendered languages without unsupervised manner is challenging because of the inner structure is quite different. To demonstrate these hardships, I used the statistical machine translation datasets, NeurIPS test and NeurIPS datasets. And to demonstrate the low resource language, you can see the token number of the Turkish is the 0.4 million tokens and 28 sentences, which is very low comparing to English. For tokenization, fast BPE is used, and transformer model is this standard 6 layers, 1024 hidden units, 8 hit Gallo activation standard transformer model with Adam optimization and linear warm-up. 20,000 token mini batches used. If there are some more resources, the token mini batches could increase, and it would also helps the get better results. But I only have one GPU, so I reduced the size. And training took a week, luckily without a loss of any electricity. I live in a place like that. And I was able to use float 16 operations to get chance of the faster training. And these are the examples. And Blue Score caught the literature and surpassed the literature from English to Turkish translation task. But to confirm, I need to do other tests, and I really look forward to learn more to do these kind of tests. Here you can see the correct examples. The target and the model translation from Turkish to English is correct as expected. And grammar is correct, words are correct. Here also from English to Turkish, these are the model translation examples. All the punctuations, even punctuations are correct. A model trained for more than 100 epochs, 150, but I can't remember. I can check for you. And these are the very bad examples when the model collapsed. And even though I tried to, I used grammarly similar in a sense of not being too complicated, it failed on pronouns because the most represented pronoun showed everywhere without any reason. And there are some other problems. It kept translation mixed. So some of the model translations are both Turkish English. So it seems model it's very wrong there. But there are some tips and tricks to increase the score and the prevent this. This is my very early and baby step work on NLP. And if there were larger corpus, it would provide higher scores. And after that, I really want to try to do experiments on low resource languages only, and also trying to non-English pairs. And if you are interested in or up to collaboration, I would love to. Thank you.